So I guess everybody is ready. So today I'm going to start power series solutions. Power series solutions. Okay, fine. But before that, I'd like to tell you something about what I did in my last class. So if you recall, in this example, while trying to solve the auxiliary equation, so there's something like 4k divided by 2, and then I told you that if m is real, so then the solution is going to be of the type your c1 x to the power m, c2 x to the power minus m. So I made a mistake here. It is not m and minus m. If the roots are m1 and m2, so then this is going to be something like this, and this is going to be something like this. Okay, please correct that. Probably you know that I did a silly mistake there. But anyway, because I was worried only about the nature of the solution. So although these statements didn't have that much significance, but still we need to be precise. Okay, fine. So this is about the correction in the last class. So now I'm going to tell you about the motivation of using power series as solutions of ordinary differential equations. But before that, I would like to do some recap of power series. Okay, fine. So now, can you tell me, like, suppose I am considering an infinite series. I'm considering an infinite series. Okay, as you probably know already that, of course, a power series, it is also an infinite series. But what is the difference between all the series that we considered earlier, which we simply called an infinite series, and these power series? Can you tell me?
The power series has a special form, that is summation a n x power n from n equal to 0 to infinity.
A n x to the power n. Okay. This is also an infinite series, but all the infinite series that we considered earlier, so what happened to them? Like, okay, so maybe I shouldn't have asked you that question in that way. Let's say here, you have to remember that, we are considering a variable x here. Okay? So let me give you the formal definition of a power series. The formal definition of a power series is that if you have an infinite series of this form, fine. So this is called a power series. In x minus a, centered about a. Okay, fine. So this is the formal definition of a power series. Okay. So now, then, as you know that whenever we are going to talk about the convergence of an infinite series, before that we have to talk about a sequence. As you know that a sequence, it is nothing but a function from a set of natural number to the set of real numbers, right? And what we do, we denote a sequence as something like this, n equal to 0 to infinity. And again, please remember that n here, n doesn't necessarily, it has to start from n equal to 0. Okay, because it is going to extend to infinity. I mean, wherever you start, you are going to have an infinite number of terms there. Okay, even if you have finite number of terms, what we can do, we can make them repeated, and in that way we can generate an infinite series. Okay, fine. So now, again, you know that convergence of a sequence. Okay, so I'm just going to briefly touch upon all the concepts that are going to be required in order to study power series. Okay, please bear with me because you may think that many of the stuffs are being repeated, but again, I want to touch upon everything so that we don't miss anything, and later on, you guys are not in trouble. If I rope in something all of a sudden, and then you may be thinking where this is coming from. Okay, fine. So the convergence sequence, as you know, that we are going to say that it is a sequence like this. It is going to, and of course, let me tell you that whenever we are talking about all these power series and sequence, let me tell you that for the time being, we are considering only sequence of real numbers. Okay, sequence of real numbers. Okay, so now we are going to say that this is going to converge to a point, say A in R, A in R. So what happens if giving epsilon greater than 0, there exists a positive integer, n such that your an minus a less than epsilon for all n greater than equal to n. So this I have already explained to you. Okay, so that is about sequence, convergence of a sequence. And again, let us come to the convergence of a power series. Convergence of a power series. It is similar to the convergence of an infinite sequence. Sorry, infinite series. And what is that? Say, suppose I am considering this power series. Suppose I am considering this power series, and then if I consider the nth partial sum of this infinite power series, which is of course it is going to be defined by I going from 0 to where?
N.
0 to n, right? 0 to n. Okay, so then it is going to generate a sequence Sn. Okay, so now if you consider this sequence, if you consider the nth term of this sequence as limit tends to infinity, so basically what you are going to get, you are going to retain this power series. You are going to retain this power series. Is it okay? Fine?
Yes, sir.
N tends to infinity for the nth partial sum, then you are going to retain the infinite power, the power series. Okay, of course, this is infinite. Okay, so now, and again, like say, when the sequence of nth partial sum is convergent, we say that the infinite power series is also convergent. So basically, that means this limit exists, isn't it? So that means this infinite sum is going to exist. That's it. Okay. So later on we are going to find out under what circumstances you can get a convergence of this infinite series, which is nothing but a power series. Okay. And I am going to relate them to the solution of an ordinary differential equation. Okay. Fine. So so this is about convergence of power series. So now there is an important aspect of the power series I'd like to tell you. Okay, so this is my fine. So this is my power series, and again say all of you are. I'm absolutely sure that you are very much familiar with power series solution. Okay, but probably what happened earlier, most of the times we were simply doing those kind of problems, quite mechanically, right? Without understanding what is happening behind. Because basically, if you plug in some power series and after that you find out the coefficients and then, like say, you find out the solution, and then probably those solutions, it looks familiar to you in terms of some elementary functions, and then you are happy that okay, like those elementary functions, they satisfy the given differential equation. That's it. We are happy. But now we are going to learn something more on that, and I am probably, like say, all the theorems related to power series solution. Probably during your BSc and MSc days, they only the statements were given. Is it so? right? Without their proofs being actually provided. Has everybody done all the theorems? I mean, the proofs of power series solution. I think since I'm not getting any answer, so that means that you haven't done it so. Okay, fine. So we are going to deal with them also. So now, if you recall what you did in solving, I mean, an ordinary differential equation with the power series concept, then what you probably did, you simply started with something like this. You simply assume that the solution is of this type, right? Solution is of this type. And of course, I'm also going to do this and don't worry about it. Okay, fine. Now, why are we doing this? Why are we doing this? Whereas my original, in my original definition, I defined the power series in this way. Can somebody tell me? Yes? Is there some link failure? Can somebody unmute and see whether you guys are still in active?
Yeah, we are here, sir.
Okay, you are there, right? Okay, fine. So, can you tell me, I mean, why instead of using this, we are going for this kind of approach? Can anybody tell me? Okay. Yes.
The second one is with respect to the center 0. So, but the
Yeah.
first one is with respect to A.
Yes, definitely. So what is happening? Say here, x equal to 0, I may plug in to be something like something like j, say, right? So then I can definitely get a power series like this. I can definitely get a power series like this, right? Because this makes my life easier. So whatever property I am going to consider here or I am going to discuss here, it is going to be about a power series for j about j equal to 0, right? So then what I am going to do, simply here what I have done, I have shifted the origin, right? Sorry, I have shifted the center of the power series, isn't it? So later on, I'm simply going to plug j equal to x minus a, and then from there, I can get all the properties, which is going to include the center of the original power series A. So basically, this is shifting of the center or shifting of the power series. That's it. Okay, fine. So you may be thinking that, like say, every time we are going to consider only it being centered about x equal to 0, but that is not the case. Even say, suppose later on we are going to do something about singular points. So suppose I have a like say regular singular point at x equal to 1. So I am going to consider a series about x equal to 0. But you have to remember that it is something for j minus 1 equal to x. Okay, fine. So that is where the shifting will be done. Okay, fine. So this is about shift. So now let us come to another concept. Radius of convergence. Yes, can someone tell me what is the radius of convergence? And suppose I am considering a series about x equal to 0. Yes. Okay, since you guys are silent, it seems to me that you guys are not really confident about this infinite series. Okay, so fine, radius of convergence. Okay, suppose I am considering this infinite series C n x to the power n. Of course, and going from 0 to infinity. So now, then, what may happen? What may happen? This series may be absolutely convergent for all real numbers. For all real numbers. Maybe. I'm not saying that this is going to be. Okay. So that may be one probability. The next possibility could be that this series converges absolutely for all mod x less than r, where r is a unique non-negative real number. Non-negative real number. Okay, it converges for mod x strictly less than r, and it diverges for mod x strictly greater than r. Then we say that r is the radius of convergence of this given power series. Is it okay? Fine.
Yes, sir.
Yes, sir.
Okay, fine. So that means what is going to happen if your r equal to 0, if r equal to 0, I'll come to r equal to 0 later. Okay. Before that, if r equal to infinity, so that means the series is going to converge for all x belonging to the set of real numbers, isn't it?
Yes, sir.
Isn't it? Fine? Okay, so that is the case. And if r equal to 0,
Then it is convergent only at 0.
it is going to be convergent only at 0. Okay, fine. So this brings me to the definition of interval of convergence. Interval of convergence. Okay, so now suppose this given series has a radius of convergence small r, So then if I consider this set, say suppose I consider this set like x belonging to r, x is a real number such that mod x strictly less than r. Say suppose I consider this set. Okay, so that means for all x lying in I, what is going to happen? This given series, this is always going to be convergent. Is it okay with everybody?
Yes, sir.
Yes, fine. So this set is called the interval of convergence. This set is called the interval of convergence. Okay, so that means if r is infinity, then the interval of convergence is nothing but the set of real numbers. Okay, fine. Okay, if r is 0, then interval of convergence is what?
Singleton set.
It is a null set, right? Is it going to be an empty set or singleton set?
Empty set.
Empty set. Okay, fine. And why we are not bothered about x equal to 0?
Yeah, I think x is equal to 0 is not an interval.
No, fine. Okay, so forget about the radius of convergence concept. Okay. So suppose I am simply considering this infinite series. So why I'm not bothered about what happens to this series when x equal to 0?
At x is equal to 0, it is definitely convergent. So,
yeah. So that is trivial. Okay, fine. So this is about interval of convergence. Then, okay, fine. See, here you didn't ask me one question. I simply talked about this strictly less than R, this strictly greater than R. Okay, I didn't say what is going to happen when it becomes exactly equal to R, right? I didn't say anything about that. And again, as I have told you, see, if my infinite series is centered at say A, right? So then the radius of convergence, it is going to be defined in terms of something like this. Okay. So this is going to lead me to something like, say, suppose this is A. So then this point is A minus R, and this point is A plus R. Okay, each of this distance, this is R. Okay, so now these are the endpoints. Okay, see what is going to happen at the endpoints. I'm not absolutely sure whether these sequences convergent or divergent. So we have to check for that. So it may so happen that there are four possibilities. Like say you may have the interval of convergence. It may be something like A minus R, A plus R. Then it may be like this. It may be like this, or it may be like this. Okay, I may have all the four possibilities. Okay, it may be, convergent at both the endpoints. It may diverge, it may converge in either of them. Okay, so for this we have to do some specific tests, as you would see later on. Okay, and again, please remember that I'm not going to do any problem specifically related to power series only. I'm going to consider them only as solutions of some given differential equations. Okay, fine. So now you know that the ratio test, right? Ratio test. So now, what was the ratio test of an infinite series? We had already done this, right, in our existence and uniqueness theorem. We have already done a certain part of this. But the thing is that we didn't, broach up the idea of radius of convergence there. Okay, so let me come back to that. Say earlier what we did, we consider some infinite series like this, and then what we say that if n tends to infinity, if limit s tends to infinity, this equal to L, then by ratio test, the infinite series converges if L is strictly less than 1, right? It diverges if L is strictly greater than 1. And if L is exactly equal to 1, we cannot say anything. We have to do certain tests. Is it okay with everybody? Right?
Yes,
Isn't it?
yes, sir.
Yeah. So now what is happening? Instead of series like this, I am considering series like this. Is it okay? Fine. So here, if I consider this as my nth term, so this particular concept, so limit n tends to infinity this is going to be my what? Your Cn plus 1 x to the power n plus 1, and then Cn x to the power n, right? And that is going to lead me with limit n tends to infinity, your Cn plus 1, Cn, this. Is it okay? Fine? So far so good, right? So now what is happening? So you know that if this is strictly less than 1, this series converges, right? Yes?
Yes,
Isn't
sir.
it?
Yes.
So that means what happens if your mod x is less than limit n tends to infinity mod of Cn by Cn plus 1, right? This series is going to converge. Is it okay?
Yes, sir.
Yes, sir.
Right? So that means this is nothing but the radius of convergence, maybe. Let me call it capital R. Small r will also do, right? Let me call it capital R. So that means this radius of convergence for series like this, it can be simply defined as r equal to limit n tends to infinity Cn plus Cn by Cn plus 1. Is it okay with everybody? Right?
Yes,
Isn't
sir.
it? Yeah, because you know that if R, this R is if mod x is greater than R, the given series is going to diverge, and that corresponds to this equation, isn't it? Fine. So that is why from now onwards, whenever we are going to find out the radius of convergence of an infinite power series, I am going to stick to this. Okay, fine. Okay, so this is about ratio test. Fine. So now the next thing what I'm going to do that is very, very significant, and you may be thinking, why, I mean, this power series solution somehow works as the solution of some ordinary differential equation. So the answer to that is going to come from this concept. So a power series defines a function. A power series defines a function. Okay, fine. So, like say, suppose I am considering this Cn as the power n. Okay, so fine. So obviously, what is happening here? This is C1, so C2 x squared, and so on, Okay, so obviously, what you can see that what we can do, like we can do term by term differentiation here because this is nothing but a polynomial. Is it okay? Fine.
Yes.
Isn't it? It is nothing but a polynomial, right? So similarly, we will be able to do term by term integration also, right? Term by term integration also. So there is a possibility that I mean this infinite series, it exactly behaves like a continuously differentiable function. Is it okay? Isn't it? Of course. I mean, I'm still not saying that it is definitely a possibility. I am saying that there is a probability. Isn't it?
Yes, sir.
There's a probability, right? There's a probability. And again, fine, say whenever you define a function, before going into its continuity and differentiability, first thing you have to consider whether it exists or not. Is it okay? Fine. Whether it exists or not. That is what defines. Yeah, that is what defines the domain of a function, isn't it? Fine. And again, you know that this series, whether it exists or not, that is going to depend upon whether, like say, of course, the series can exist. The series can exist. But if the series acting as a function is to exist, then it must exist finitely, isn't it? That means it must exist as a convergent series. You got my point, right? So that means there is a possibility, we are moving towards almost 95% possibility that this series can act as a function which is nothing but the solution of an ordinary differential equation if it is convergent. Is it okay? Right? So then, say the interval of convergence and interval of definition is going to be the same. Is it okay? Fine. Interval of the definition,
Yes,
right, of the solution of a differential equation, and if you are considering a series as the solution of an ordinary differential equation, so there is almost 100% possibility that I am moving from 95 to 100 now. Possibility that that is going to be the solution of an ordinary differential equation, and the interval of convergence is going to be the interval of definition. Right? Okay. So, so now the next thing I am going to do, that is a pretty mechanical stuff. Okay, but please be attentive about this, because later on I am going to directly substitute that expression when I'm going to work out some examples. Okay, so please have a careful look at what I'm going to do now. Okay, so and again, I know many of the students, they simply hate this power series because they find the summation stuff. They find the summation stuff very cumbersome. In fact, it is not. You have to get rid of that idea that, oh my God, it is extremely difficult. It is so complicated. No, you just attack it systematically. Everything is going to be all right. Okay, fine. So what I'm going to do, I'm going to now do this multiplication of two power series. See the index of this. These are very important. How you manipulate these indices. Okay, fine. Say, suppose I have two power series like this. Okay, fine. And I'm trying to multiply it. Okay, so now if I expand it, so this is simply okay. So similarly, this is B0 plus B1x, B2x squared, B3x cubed, and so on. Isn't it? Fine. So far so good. So now let us bring similar power of x under one umbrella. Okay. So the very first thing, you know that x to the power 0, I'm simply going to have a0, b0, right? Okay. Then x to the power 1, See, if you look at this, a0, b1, right? That is one thing. Is it okay? And then a1, b0, this into x. Is it okay? Fine. Okay. So then.
Yes, sir.
Then thank you. So then what about x squared? See, for x squared, I have a naught b2, a naught b2, then a1 b1, then a2 b0. Is it okay? Fine. So in this way I can go, right? So that gives you an idea that for x to the power n, what I am going to have? Yeah, you tell me. A naught
Bn.
bn plus a1
Bn.
bn minus 1. So in this way, finally I am going to get a
An.
yeah a n minus 1 b1 plus a n b naught. Okay, fine. Is it okay?
Yes.
Everyone is comfortable? Fine. So that means now if I again write it as an infinite series like this in terms of powers of xn, then what I can do, I can simply write it like, say suppose my xn will be here, but here I am going to use a summation. The summation is going to be k from 0 to n, then a k b n minus k. You see whether that is fine or not. Is it okay? This is very important because later on I will substitute it. Then you should figure out where this has come from. This has come from here. Okay, so simply k going from 0 to n and ak b n minus k. That's it. Okay, so this I am going to use very frequently later on. So this is about multiplication of two power series. So now let me come to the concept of analytic function. Yeah, you tell me, when is a function say f of x? This is said to be analytic.
If it's said to be analytic at a point A, if it has a power series representation around A.
If it has a
Power series representation around A.
Okay, so basically it can be expressed as c and x minus this n equal to 0 to infinity. So basically a convergent power series. Okay, if it can be expressed as a convergent power series about x, that's it. Okay, fine. So this is about analytic function. Now another important manipulation I'm going to talk about, and that is nothing but the shifting of the index. Please be attentive. Shifting of index. This is very important, and I have seen many students, they just simply try to memorize something about this addition of power series, and then later on they fumble. Okay, so just let me consider this summation. Say n equal to 2 to infinity, n into n minus 1, cn x to the power n minus 2 plus n equal to 0. Okay, cn x to the power n plus 2. Okay, fine. Yes. Now you tell me how to go about adding this, what is the first thing you are going to look at when you are going to add these two series? Yes?
We'll make the index equal.
But why that is so? Why that is so? My point is that. Why that is so?
We want to have the same power. If we want to add in, the power should be same, and corresponding index we should change.
Okay, fine. That is fine. So what she is saying is that see here I have power of x is n minus 2. Here I have power of x n plus 1. She said that I should try to sum it up in such a way that both the powers become the same. That is fine. That we are going to tackle a little bit later on. But the thing is that the very first thing you have to look for is that whatever number of series you are given, you have to look at where the series is starting, with which power of x it is starting. That should be your first thing. Is it okay? For example, if you look at this series, n equal to 2, right? N equal to 2. So that means if you plug in n equal to 2 here, this series is going to start from x to the power 0. Is it okay? Is it okay to everybody?
Yes, sir.
Yes, sir.
Similarly, here it starts from n equal to 0. Now, if I plug in n equal to 0 here, this series is going to start from x to the power 1. Isn't it? Right? So that means this series is going to have one extra term. Are you getting my point?
Yes, sir.
Right?
Yes, sir.
See,
Yes, sir.
now look at these two. It may seem that, oh my God, this is starting from 0, this is starting from 2, right? So definitely this is going to have more number of terms than this series, but not. Fine? That is the first thing you will have to look at. So what we are going to do, we are going to make both the series start from x to the power 1. That is the first thing. Because I cannot make this series start from x to the power 0. You got my point? Right? So that is why the very first term of this series, I am going to take it out. Okay? So the very first term, if you plug in n equal to 2 here, so it is going to give you 2 into 1, and then C2, right? And then what is going to happen? What is going to happen? This is going to start from n equal to 3 to infinity, n into n minus 1, Cn x to the power n minus 2, and then this part is same. This part is same. That n equal to 0, Cn x to the power n plus 1. Okay, then I can guarantee you that now if you do shifting of the index, like say if you are going to make both of them same, then what is going to happen? These indices are also going to start from the same. I can guarantee you that. Okay. For example, now what I'm going to do here, I'm going to make it say n minus 2 equal to p. If n minus 2 equal to p, then what is going to happen? Then corresponding to n equal to 3, p is going to be
1.
1. So this is going to start from p equal to 1 to infinity. So n has become p plus 2. So this is going to be p plus 1, and this is going to be c p plus 2 x to the power p. And then again now here you plug in n plus 1 equal to p, then when n equal to 0, p equal to 1, right? Isn't it? And from here, if n plus 1 equal to p, n equal to p minus 1. So this is C p minus 1 x to the power p, right? Is it okay with everybody? Fine? Is it okay?
Yes, sir.
Yes, sir.
Yes. So now you see, like this p, it is just a dummy suffix, isn't it? Whether I can use p, q, or whatsoever, I, j, k, it is always going to work, isn't it? So what I am simply going to do, I am simply going to change it to n now. Even p is going to work, don't worry about it. This is n, this is n, this is x to the power n, this is n, n, n. So now what I can do, I can bring both the series under one umbrella. So eventually this is going to be 2c2 plus n equal to 1 to infinity, then n plus 2, n plus 1 cn, cn plus 2, right? N plus 2 plus cn minus 1 x to the power n. Yeah, is it okay? Fine. So this is the way we are going to proceed. And let me tell you, let me give you some warning. Like in Simon's book, I have seen that while working out, I mean, summation of series like this, they have directly jumped into, he has directly jumped into something like this, which I don't agree. Which I don't agree. You should always follow this procedure. You should always follow this procedure because what happens, like say you will be left with some terms, okay? So when you are going to equate the different powers of x, okay, from the general term, some relations are going to come out, and from the terms which you have taken out, some relations are going to come from that. It is not necessary that whatever is outside this summation, it is exactly going to follow the same pattern, whatever is inside the summation. So that is where we have to be a little bit careful about it. Because I have seen that he has worked out some example, directly he has jumped into this formula, but you please don't do that. Okay, you always follow this thing. First thing you got to notice is that where is the powers of x starting from? Where is it starting from? Okay, if all the power series they start from the same power of x, we are fine. You can directly move ahead of shifting the index, right? But if they are not, then what you have to do, you have to take some powers of x out separately, and then you have to bring all the other terms under one umbrella. Only there you make this shift of index. Is it okay? Fine? Is it okay?
Yes, sir.
Yes. So we
Yes,
are going
sir.
to follow this rule. Okay. So now I will come to. So I think we have done our groundwork about power series. So we have enough knowledge now. So we can proceed. We can proceed by considering power series as our solution. Okay. Fine. Okay, fine. So now you may be thinking, like, what is the motivation? What is the motivation of using power series as the solution of ordinary differential equations? Okay. So now, I mean, you have come across like say second order linear differential equation of this form, I mean reduced to the normal form. Okay. So then we have seen that it may be of this form or it may be like say non-homogeneous also. We don't need to worry about that part. So now, like whatever we have done so far, like the solutions, that if they are in the form, like say, as a function of say e to the power x, sin x, cos x, some polynomial, or say LMS. If they are a combination of these kind of functions, and these functions are nothing, they are simply called elementary functions. So if they are in terms of elementary functions, so we can easily find out the solutions. Okay, but it may not be so every time. So what happens that, as you know, like the differential equation. In my very first class, I told you that the motivation of studying differential equation comes from the mathematical modeling part. Okay, like say we mathematically model the real life situations, and after modeling it through differential equations, we try to solve it, and we just try to put them into work, right? Now the thing is, the differential equations that are going to come out of mathematical modeling. So it may be sometimes something like this. It may be something like this. Okay. In those cases, you will see that this elementary function approach, it is not going to work. Elementary function, it is not going to work. Okay. But later on, we are going to see that. I mean, say suppose our differential equation is such that these coefficients of this y prime and y, that is px and qx, if they are analytic functions, or if by somehow they can be made to behave like analytic function, so then we will be able to solve equations like this in terms of infinite power series. Okay, so that is where the motivation of using power series as solution has come. Okay, so now let us see whether it works or not. Okay, so I am giving you a very this one. You already know what the solution is, right? Let us see whether power series solution works here or not. Okay. So for that, what we are going to do, we are simply going to assume that okay, let your y equal to your this and equal to 0 to infinity. Right? Okay. So then your y prime, it is going to be what? N a n x to the power n minus 1, right? N equal to 0 to infinity. Okay? Yes or no?
Yes, sir.
Yes.
No, sir.
No. The answer is
N
no.
equals
Why?
to 1, 2. Yes,
N
sir.
equal
N
to
equals to 1, 2.
1 to infinity. Okay, n equal to 1 to infinity, because see your okay, once you differentiate it, then you are going to get a1 plus 2a2x and so on. Okay, so then it is going to start like this. Okay, fine. So now if I plug that in here, then what I have, n equal to 1 to infinity, and a n x to the power n minus 1 minus n equal to 0 to infinity, a n x to the power n, this is equal to 0. Okay, fine. So now let us look at the two individual series. They start from what power of x? This one, it starts from
x to the power 0.
x to the power 0. This one,
X to the power 0.
x to the power 0. So that means we don't have to take any terms out. Is it okay? We
Yes.
don't have to take any term out. So basically what I'm going to do, I'm going to plug in n minus 1 equal to p. That is going to make me when n equal to 1, p equal to 0, right? So I'm writing n equal to 0 to infinity. So n minus 1 equal to p means n equal to p plus 1. So basically I'm going to substitute n with n plus 1. Okay, so then this is going to be x to the power n, right? It is going to be x to the power n, right? So this is already in x to the power n. It has started from n equal to 0. So what I can do, I can simply write it as is it okay with everybody now? Yes?
Yes, sir.
Right? So now see here it was straightforward. Here it was straightforward. So now if you equate, I mean the nth power of the see here if it has to this is equal to 0, the coefficients of the nth power of x they have to be 0. So that is going to give you your n plus 1 a n plus 1 minus a n. This is equal to 0. And see here I have started n from 0 to infinity. So this is for all n greater than equal to 0. So that means this is going to give you a recurrence formula an, right? So then if you plug in n equal to 0, 1, 2, etc. So n equal to 0 is going to give you a1 is equal to a0, then a2, maybe I'll write it here. Okay, a2 equal to, if n equal to 1, then this is half a1, a3 equal to 1 by 3 a2, so that means 2 into 3 a0, and so on, right? So that means I have already assumed y equal to this, right? So I have expressed everything in terms of a0. So this is going to give me a0 1 plus a1 was again equal to a0. This x squared by factorial 2 plus x cubed by factorial 3 and so on. So what is this? That series, is it, do you recognize that series?
E to the power
e
exponent.
power
This is
x.
e to the power x. Okay, so definitely you know that if you plug this in here in the differential equation, this is going to act as a solution, right? This is going to act as a solution. Okay. Now the question is, does it always work? Does it always work? For example, okay. Now, I want you to try this at home. You again start with an infinite series like this. You again start with an infinite series like this. Then you proceed, and again you are going to end up with some combination of elementary functions. So combination of elementary functions like maybe it is a linear combination, maybe it is some non-linear combination also, right? So then you see that whatever solution you get in terms of elementary function, that is not going to satisfy the differential equation. Okay, so that means it is not always going to work, right? So we have to impose certain conditions somewhere. Okay, and again, it is not necessary that every time your series solution is going to be such that it is recognizable as an elementary function. Okay, So let us take one example, and I am going to finish my class there. So basically, what it tells you that we may not always be lucky enough. We may not always be lucky enough to get a series solution which is convertible in terms of an elementary function. Okay, so now I will move to solving second order linear differential equation. Second order linear differential equation using power series. Okay. So what we are going to do, we are going to consider, say, suppose I am considering an equation of the type this. Zero. Okay. So now, obviously, if a2x not equal to 0, a2x not equal to 0, then this can be put in this form. It's not right form. Qx y equal to 0. Okay, fine. So now let us come to the definition of your ordinary and singular points. Okay. So does anybody recall the definition of those kind of points? Yes? Okay.
Singular
So, yes. Yeah, proceed, please proceed.
if we a point is said to be singular point for a function if there doesn't exist any power series expansion around that point.
Okay. Why start with something negative? Let us start. let us start
Sir,
with something positive.
at those points where the px qx functions are analytic, those points are called ordinary points, and where those are not analytic, those points are called singular points.
Singular points. Yeah. So basically, a point x equal to x naught is called an ordinary point. An ordinary point for this differential equation A if both Px and Qx are analytic, both Px and Qx are analytic about the point x equal to x naught. So that means we should be able to find power series solution of the type of this type or Px and Qx. So that means Px and Qx are expressible as convergent power series like this. Is it okay? Otherwise, x naught is called a singular point. That's it. Okay, fine. So this is about regular point. This is about, sorry, not regular point, ordinary and singular point. So now I just want to give you one example where like say the power series solution, you may not get it in terms of some elementary function, or you may not be able to convert eventually it into some combination of elementary function. Okay, fine. So let us take one example. Of course, P is non-negative. Does it ring a bell? What is this equation? Yes, what is this equation? Okay, I'll come back to what is this equation later on. Maybe, I mean, while I'm working it out, you'll be able to recall. Okay, so now, see, let me call it 1. Let me call it 1. And if I reduce it to normal form, what I'm going to get, this is going to give me right? So that here your px equal to and minus 1. Okay, fine. So can you give me, I mean, what are, ordinary points and singular points for this equation? I mean, equation number 2. Yes? Okay, let us start with the
All
negative.
points,
If
What are
x
the
not
singular
points
equals to
except
plus
1 and
minus
minus 1.
1, these are ordinary points.
X equal to plus minus 1 are ordinary points.
Except
No, singular points.
No, x not
Which points
equals to
are-
plus minus.
It is singular points, right? Okay, so all other points belonging to the real line except these 2 points, they are ordinary points. Is it okay? Fine? Isn't it? Okay, so that means, see, I'm still not sure, but I have some strong hunch that okay, if I mean px and qx, I mean they're analytic about a point, okay, and if I am seeking a solution of this differential equation in the form of an infinite series about that point, which is an ordinary point, because by definition the px and qx, they are analytic about that point. So probably it is going to work. It is going to work. And let me guarantee you that there is a theorem which is going to guarantee you that this happens. Okay, so that I'm going to prove tomorrow. So now, obviously, your x equal to 0 is an ordinary point here, right? Isn't it? Because px and qx are analytic about x equal to 0. Is it okay? Fine. So that is why I am seeking, although it is still a strong hunch, I still have to prove. I am, okay, I am considering a solution of this form. Okay, so I am going to substitute it where? I am going to substitute it in 1 or 2. Hmm?
1.
Yeah, if I substitute it in 2, it's the same thing. But 1 is going to make your life much easier. Okay, so let me substitute it in 1 because you guys already know what is going to happen. So second order derivative, it is going to be n into n minus 1 a n x to the power n minus 2, isn't it? Now n goes from where to where? Second order derivative.
2 to infinity.
2, yes, 2. So then minus 2x, I know it already, and an x to the power n minus 1 plus p into p plus 1, and again n equal to 0. And again, please don't forget to write where n goes from where. I have seen while evaluating the answer sheet that many people, because initially they are not very confident, they don't write anything here. Okay, simply infinity they write here as the upper limit, lower limit, they are silent about it. Okay, fine. So although the first few lines they are going to be lengthy, later on I am going to make it compact, don't worry. So let me break it into 2 parts. Okay, let our root be long, distance we are going to travel, but we have to understand it clearly. Okay, so it is going to be, sorry. An x to the power n minus 2, then minus 2 to infinity and to n minus 1, an x to the power n, and then this one minus 2 n equal to 1 to infinity and an x to the power n, okay, and then like, okay, p into p plus 1, an and equal to 0 to infinity. Okay, fine. And don't jump into excitement, because I mean, oh my god, I am getting like for all these three series, the power of x is simply n. Don't get too excited about it. Okay, think about the very first task that I have told you. What was it? Firstly, check what is the lowest power of x in each of those series. Okay, so here obviously lowest power is x to the power 1,
0,
0. Here
2,
2.
x to the power 2.
Here 1. Here again 0. Right? Okay, so that gives you an idea that I have to start all the series from x squared. Isn't it? Fine. So then what I'm going to do, so I'm going to bring x to the power 0 and x to the power 1 out of the series. Okay, fine. So from the first series, if I take out x to the power 0, plugging in n equal to 2, this is going to give me 2 into 1, k2, into x to the power 0. Okay, so then x to the power 1, 3 into 2, then a3x, right? 3 into 2, a3x. And here this series is fine. This series I am not going to do anything. Let it be like this, n equal to 2 to infinity, n into n minus 1, an x to the power n. Here I'll have to take out x to the power 0 term. So this is going to be minus 2. Then if you plug in n equal to 1, 1, a1. So simply 2a1 x, because if n equal to 1, this is x, and then let the remaining series be as it is. So now n is going to start from 1. N is going to start from 1. Now here
2.
2. Just a minute. N is going to start from 2. Okay, so see, and one thing I will say, this is nothing but this series, right? Here from this series I have taken these terms out, right? What about the other? So others are going to be n into n minus 1, an x to the power n minus 2, and n is going to start from where to where? Now I have taken the first two terms out of this series.
4,
N equal to
4,
4. Fine. So then again here also I have to take out two terms. So plus p into p plus 1, and then first two terms are here, a0 plus a1x, and then plus p into p plus 1. As before, this is going to start from 2 to infinity, an x to the power n, this is equal to 0. So now I will define, don't worry about it. You will see that I'm going to get all similar power of x, and again n is going to start from the same index. You don't need to worry about it. So now, okay, so from here, let me take similar powers of x. So this is 2a2, and from here I am going to get p into p plus 1 a naught. Okay, then here I am going to get 6a3, from here minus 2a1, and from here plus p into p plus 1 a1 into x. So now let me concentrate on the other terms. Okay, fine. Okay, fine. So now look at this. Okay. So now what I'm going to do, I'm going to plug in n minus 2 equal to p, right? So n is going to be equal to p plus 2. When n equal to 4, p equal to 2. So basically here n is going to start from 2 to infinity, and then for n it is going to be n plus 2, n plus 1, and then a n plus 2. Is it okay? Now see what I'm going to do. I am going to loop in x to the power n here. Okay, and you will see that it is going to work. So this term is done. Is it okay with everybody?
Yes, sir.
Right? Here I
Yes,
have
sir.
made shifting of index. See, simply think about n minus 2 equal to p. Okay, when n equal to 4, p equal to 2. But instead of p, we are simply going to start with n equal to 2. Okay, and here it is already n equal to 2. I don't need to worry about it. So this is minus n into n minus 1 an. And here also it is n equal to 2. So it is simply minus 2n an. And here also n equal to 2. P into p plus 1 an. Okay. See, as I promised you, see, the index is going to start. It is going to start from the same index, and the powers are also going to be the same. You don't need to worry about that if you follow this convention. Is it okay with everybody? Fine. So what I'm going to do, I'm going to stop here. I'm going to stop here, and I'm going to resume from this part tomorrow. This part tomorrow. And let me tell you that I had sent you a mail regarding your 2-hour exam. So I'm going to discuss about it tomorrow. So obviously, there's one student, Vikramjit. It is clashing with his class timing. So maybe we will find some other stuff. Don't worry about it. Okay. So maybe we'll shift it towards the evening, or we can go for 12 to 2 also, if that is fine. So we are going to discuss about it tomorrow. Okay. So then I'm going to meet you tomorrow.